Hello, everyone, to another OCP Tap call. This is call number 109. And we have today Professor Milano. Professor Milano is an assistant professor at Princeton University working at the intersection of programming languages, distributed systems, and databases. Her work has appeared at top-tier academic venues and is now running on millions of Apple devices. She's a recipient of the NDSEG Fellowship and has won several awards for her writing and services. And today's talk is about programming distributed systems, and hopefully, like, we can have some subsequent presentations about like where we can build on top of it, right? Again, I'm not putting you on the spot, but hopefully, after we give her a good experience here today. And so, with no further ado, the floor is yours.
Sounds great. Can I actually ask, for a small amount of further ado, what's the sort of question protocol you guys are used to? Do people interrupt? Does it come in the chat? Do we have some time at the end?
Yeah, very good to bring up. So usually we don't interrupt you while you go through the talk, and then at the end we'll have a session for Q&A.
Okay, sounds good.
Unless you want a different configuration.
I can be chill with basically anything.
Okay.
I'm very used to the academic market in which people are just like, wait a second, didn't I write that 16 years ago? And your entire talk is derailed. So
No.
anything is good for me.
And then we usually have also the chat. So things go there. I'll keep an eye on that because some might be on a connection without a microphone or something.
Sounds good. I've got everything open up.
Wonderful. Let's get the floor going.
Okay. Well, thank you for that wonderful introduction and also the clarification about the way the questions will be handled. Like we just heard, my name is Mae Milano. I'm a professor at Princeton, and I'm here to tell you about programming distributed systems. And let me start by saying that programming distributed systems is hard. The modern world has seen an explosion in both the ubiquity and the sheer scale of systems in every domain. Applications that used to be like local single-threaded things that would run on my one computer, like a word processor, say, have become concurrent or distributed or even geo-distributed. And as our systems have scaled, our ability to program them has not kept pace, forcing programmers to keep in mind ever-increasing layers of complexity. The results are predictable, a seemingly endless parade of bugs and vulnerabilities as programmers wrestle with each new leak in what were once reliable abstractions. This is basically where we are today. We've built a cloud, yes, and it's great. It provides services that we never could have had before, but we still don't really know how to program it yet. Our abstractions need to catch up. We need to build new programming languages and design new systems that make the job of building distributed systems more feasible again. So that's where I come in. Over the course of the next some amount of minutes, probably somewhere in the 40-ish range, we will be hearing a little bit about my research over the past few years in building distributed systems. Throughout my work, we'll see that careful design allows new languages and new abstractions to not just eliminate these sources of bugs, but to build better systems in the process. But before I can get into this work, I should lay some groundwork and preliminaries. And my apologies if I'm just sort of telling you guys things you've known for 30 years, but let's go over a little bit about what a data race is, what coordination overhead I'll be solving in my work, and what sources of consistency errors we're going to run into. Okay, so first, a data race occurs whenever two or more threads simultaneously access memory and at least one is a writer. A classic example of this would be, say, a split increment. Under this example, two different threads are competing to increment a value in the same location, say inside this hexagon here. One of our threads will read the initial value, and while that thread attempts to write, the other thread will race it with another read of the initial value. As a result, one of the increments appears to be lost. We're assuming here the programmer actually intended for two increments and didn't want this racy behavior. This is an example of a destructive data race, a data race that causes program errors. It's a classic example of failing to adequately reason about time in a system. It also has a bunch of commonplace solutions. I mean, we've known about destructive data races for 50 years, probably longer. And one particularly common class of solution is a transaction. So a transaction allows you to provides an abstraction where you can have a unit of code that appears to execute all at once. So the entire orange or the entire gray thread will go all at once. And while it does provide the semantics you want, it can be kind of expensive, especially if you're talking about doing local machine or small network work. We'll put a pin in that and get back to it later. But for now, let's just say we've defined a data race. The next 2 points I'm going to kind of address in tandem by talking about consistency and the coordination required for it. So when I talk about consistency for this talk, I'm mostly talking about a notion of memory consistency in a distributed storage system. This basically governs any replicated storage system, and it's a series of rules that say if I were to perform a write at one location and then subsequently perform a read at some other location, what value am I allowed to see? How does the things I'm writing relate to the things I'm reading? The strongest practical such model is something called linearizability. Under linearizability, if I perform a single write at one location and I wait any amount of time, infinitely short, and then perform a read at a subsequent location, I'm guaranteed that the effects of my write will have propagated to all other locations before my read executes. This is basically exactly the semantics you would want in an ideal world. It lets you ignore the replication entirely. Go back to pretending like we just had one machine and that consistency wasn't really a question. But it's quite hard to implement efficiently. It tends to work out pretty well on small scales where machines are close together, like say on certain well-named Greek islands. And implementing this well, especially in larger contexts, will be most of the sources of coordination overhead that we're trying to avoid. All right, now let's talk about consistency errors. Like I mentioned, linearizability works well on smaller scales, when machines are really close together, when there aren't that many different machines, when machines are relatively homogeneous in their capabilities. But when you want a database that's replicated on larger than a single island, say an entire world, you have to contend with some unfortunate physical realities. As it turns out, the speed of light is surprisingly slow. It's only about 4 inches per clock cycle. At global scales, we will have literally outgrown traditional protocols meant to ensure a consensus, like Paxos, and also traditional small Greek islands, like Paxos. And we'll have to accept the fact that our replicas will temporarily diverge. The question winds up being, what are we going to do with that divergence? So for about a decade, there was a wave of systems research that said that we will pass that divergence on to the user and crisply characterize what kind of divergence they can expect. And this corresponds to a whole host of systems operating under weak consistency models, lots of different weak consistency models. Under weak consistency, if I perform a write at one replica and I wait any amount of time, could be years, and perform a read at another replica, I don't necessarily have a guarantee whether I will be able to see the effects of my write. While I know my write will eventually propagate to all replicas, that may be after my subsequent read, no matter how delayed my read is. You get this kind of weird time travel behavior. In fact, the database that I'm using as an example here, TARDIS, is named after a time machine. And that kind of behavior turns out to be very hard to program against and leads to our consistency errors. Okay, so now we've seen our 3 problems. Let's talk about solutions. Also, if someone wants to pop a question in the chat because this was super unclear to them, it will make less sense as I go on. So I'll keep an eye on this and happy to take them. All right, we're going to start by looking at how to solve consistency errors. And I'll start by observing that some applications are capable of tolerating weak consistency just fine. Consider, for example, that I'm running an online game service, a matchmaking service, where I'm going to want to enable 3 main applications. I'm going to want to take players and match them according to their skill levels. I'm going to want to be able to record who wins and loses various games. And every now and then, I'm going to want to hold a tournament where I invite the 10 best players in the world to compete for honor and glory. Some of these services are okay under weaker consistency. For example, I'm kind of okay if it takes a few minutes for the entire world to hear that I've beat someone in a random game of Super Smash Bros. Online. I don't need my glory broadcast instantly. But others clearly seem to need a stronger consistency than that. if I say I'm inviting the 10 best players in the world, I better have a way of measuring that, a way that everyone agrees with, and that is consistent across all replicas. I built new programming languages for transactions that's intended for applications just like these, where different operations require different levels of consistency. It's a paper in PLDI. Let's now see how it works. Okay, going back to our example of running an online game service, we want to record wins and losses, play tournaments, and get match made. So let's start by making a few tables for recording this information. A wins table that records our wins and losses, a wins table that records our wins, a losses table that records our losses, and a rank table that will sort the players by how good they are in the world. And we'll use that for our tournament in the end. We'll also want some transactions to implement our operations. Something like a match transaction where we take two players, we record which player has won and which player has lost. I'll pause here and say that whenever I put code on the slides, I'm expecting that we'll be able to read the code. I tried to take great pains when designing these languages to make the code familiar to someone who's programmed in C++ or Java before. And also, all the code that you're going to see is pretty much real code. There might be a comment or two elided, but this is order of the same complexity that you as a programmer would write down when using my systems. Okay. Because of that, I also think that we might be able to read the code. And sometimes I will take some pausing, say some words that you don't necessarily need to hear, like the ones I'm saying right now, to give us time to read the code. All right, moving on. We have one transaction that records the results of a match, and we have another transaction that corresponds to inviting to the tournament. This one's a little more complicated. We start by creating a list of the best players in the world. We then grab the first 10 elements off of the rank table, stick it in the list, and return that list. And that'll be our source of invitations. You might also notice that these transactions have been annotated with the words weak and strong. This corresponds to the intuition we had earlier in our example, saying that some of that our match recording could probably tolerate weaker consistency, but our invitations could not. MXC will use these programmer-provided annotations to determine what sort of consistency the underlying storage needs. For example, recognizing that the wins and losses here are okay with weak consistency and so can be placed on weakly consistent storage, whereas the rank here needs strong consistency and so goes on strongly consistent storage. Okay, so far so good, but also pretty common. This is basically exactly what a traditional database having multiple isolation levels already provides us. So where MXC really starts to shine is in recognizing that consistency composes across transactions. Let's now look at a third transaction with much larger font that relates the wins and losses and the rank by calculating the rank based on the wins and losses. So how this one's going to work is first we're going to make a list that contains the ratio of wins to losses for each player. Well, that will contain it. Then we're going to iterate through all the players in the world. We're going to check the divide the wins by the losses. And we are going to add the result of that to the win-loss ratios. After that, we'll sort the win-loss ratios by the ratio, and we'll use that in that order to repopulate the rank table. Okay, slightly more complicated transaction, but still kind of straightforward. It also includes a bug. Now, I'm going to suggest we break with protocol very, very slightly, and I'll give you guys about 30 seconds to stare at this code and either just interrupt me or speak in the chat if you can spot a bug. I know of two. There could be more. I will say random words during this 30 seconds, so it's less awkward for us to just be sitting here reading code, but these are unimportant words. It's definitely code reading time.
Would the losses P be 0 divide by 0? I'm a hardware guy, right away I spot that.
Yeah, so that's one of the obvious errors. That's not the error that's important for the talk. It's easy to fix, but it's not easy to fix while keeping this to fit on one line. So we're just going to stipulate for the purpose of presentation that everyone loses at least once. Is this atomic? So in the world of MXD, the transaction keyword at the top here says we are going to run under a transactional mechanism, which means we're going to reach out to our replica and we're going to ask that replica to introduce a atomic transaction for this code. So it is atomic, but the error winds up coming close to that, because what I said was we're going to reach out to the replicas, and in particular the execution model for transactions in weakly consistent systems, which is inherited by MXT, is that each transaction will run on a single replica and its effects will be propagated to all replicas. When that interacts with weak consistency, you wind up having a problem. See, when I am talking about running on one replica, I have to remember that there are lots of replicas, and that under weak consistency, those replicas don't have to agree. The one replica that executes the calculate rank transaction, therefore might, even if it is atomic, completely atomic, that replica stops the world, nothing happens at that replica. Even if it's globally atomic, it broadcasts to all replicas, stop the world, don't do anything now, I'm turning off the network until I finish this transaction. It's still not up to date. The other replicas still could have had previously committing transactions that they just didn't decide to synchronize, because nothing on weak consistency requires they do so. Thus, our calculate rank transaction might be running on effectively stale data, while our subsequent invite to tournament transaction will run with strong consistency on a strongly consistent database, as requested by our programmer. By then it's too late. We're not going to get the 10 best players in the world. We're going to get the 10 best players that happen to be closest to replica 2. We're also going to get a lot of angry emails from players that wanted to think they were the best in the world and have justified that by views of their own local replicas. What we see here is sort of a violation of composition. It wasn't enough just to run the strongly consistent transaction atomically under strong consistency. We needed to make sure that the entire derivation on which that transaction was based managed to maintain consistency throughout. Or to put it another way, strong outputs must actually stay strong. They cannot be influenced by weak operations. MXT, the language, and the compiler will automatically recognize this kind of improper influence at compile time and reject the calculate rank transaction explicitly because it allows one of these bad flows. Now, let me take a detour here and say that while I've been saying things like weak and strong consistency throughout the talk, those are really categories. In practice, there's lots and lots of different consistency models. And when I've talked about weak consistency, I'm mostly just using the properties of eventual consistency. Strong consistency, meanwhile, basically corresponds to linearizability. But there's a whole world of different consistency models here, all of which can be sorted by strength. And it turns out, at least as of 2016, that all the consistency models in common practice were at least as, that linearizability was stronger than all the consistency models that were used in practice, which is to say, if you took a system and you replaced it with a linearizable one, the system would not get less correct. Similarly, eventual consistency was weaker than all the models used in practice. That is to say, everything guarantees at least what eventual consistency would have guaranteed. This is very convenient for us because it means that our consistency models are going to form a lattice and that we can define improper influence. That it's a guaranteed problem if a less consistent read, something up in the lattice, influences a more consistent write, something down. It's also a problem if two incomparable points influence each other. The insight of my research is that we can prevent this kind of improper influence via an information flow type system, which is something commonly found in the security literature used to protect data integrity and confidentiality. And here we're basically reinterpreting integrity as consistency. Let's look through this transaction and see how using a static information flow will catch our error. Well, we'll start with ground truth. From other transaction labels, we know that the rank is on strongly consistent storage and that the wins and losses are on weakly consistent storage. We can also see, just by looking at how the flow of the program works, that the win-loss ratios is populated by reads from a weakly consistent storage. And we can then see that the win-loss ratios itself is read into the rank. This drives a contradiction. We've inferred two different labels the rank has. One coming from a different transaction must be strong, one coming from this transaction must be weak. At this point, MXD will tell the programmer, hey, this is a problem. But it's not that we're saying, I'm sorry, you simply can't run online game services, or that we're denying applications like Facebook could ever work. Rather, we'll provide the programmer the opportunity to fix this. For example, we could fix this transaction by introducing some kind of quorum read operation, which checks and merges state from all of the weakly consistent replicas when reading the wins and losses. This corresponds to effectively a dynamic upgrade for the consistency of reads. The steady state system is inconsistent, but if I'm willing to pay the high runtime cost of actually serializing all the pending transactions to weakly consistent state and synchronizing the various replicas for the purposes of this transaction, then at least for the duration of the transaction, the effects of reading that storage is actually consistent. And MXT will recognize that, allowing us to label the entire transaction as strongly consistent. If any of you are familiar with the security literature, you might think this looks like declassification. It's very different from declassification because it actually has a runtime effect, and we can talk about that during the discussion section. I should also note that flows in the other direction in the lattice, following the arrows, are totally fine. You can, for example, send email in response to running the invite to tournament transaction, and we all know that email delivery is not very consistent. So what have we learned so far? By preventing improper influence via information flow, MXT can yield reasonable semantics for mixed consistency transactions. We managed to get that important property, that strong observations stay strong, or a strong observer will only ever witness strong behavior. And while I am mostly talking to you about the compiler here, there is an underlying system for MXT and for everything that I'll be talking about in this talk. Our particular implementation is a deep embedding in C++ using far too many phrase expression templates. It's built as a shim compatible with existing databases, supports multi-consistency transactions, and is implemented in about 15,000 lines. You can download it, check it out on GitHub, but I should warn you, it's about 15,000 lines of heavily templated C++, and it's researchware. So it is fairly likely it will be a journey to get it to compile. Okay, so that's sort of the MXT story. But when we started the MXT story, we started by saying, we're going to take a world where we know that some transactions are weakly consistent and some are strongly consistent, and make sure that those things work well together. But now I want to take a step back and say, how did we know that? How are we sure that we actually got it correct when we said that the wins and losses could be recorded with weak consistency? Or to put it another way, can I figure out sufficient conditions under which I can guarantee that a program or a selection of a program is safe to execute under weak consistency? Can I find a way to get rid of the need for programmers to provide labels and just analyze the code to determine which portions of it can be run under weak consistency? And that is going to be the next section of the talk. This section is going to focus on using reliable observations for building correct code under weak consistency. Okay, let me tell you what I think reliable observations are. So in my parlance, reliable observations form a guarantee about a distributed state. This is not like some term of art that's popular in academia. I just made it up for the talk. So what is a guarantee about distributed state made by an observation? Well, it could be something like reading a constant, or it could be running a consistent transaction. For the duration of my consistent transaction, I have the guarantee that the things read in that transaction actually reflect the effective state of the database at the point at which my transaction commits. So that would be a reliable observation. But there are some other observations that are reliable without needing a consistent transaction. For example, in my example, we could see that the wins of a particular player are at least 15. This would be a reliable observation because we actually know the entirety of our application. We know that across all the code, We only ever increment our wins. There's no cheating here, so there's no needing to claw them back. In other words, no concurrent mutations are able to violate this observation. There's sort of a general class here, that the more you can restrict the mutations, or the more you understand about what mutations may occur to your data, the more general the observations you can make on that data while keeping those observations reliable. It's a spectrum. On one end, you have things like constants, and on the other, you have things like multi-writer registers. But in the middle, we've got an interesting class of objects, things like counters that are only ever incremented, or sets that we only ever add to. These objects grow monotonically. They get bigger with respect to some natural order, like less than on the integers or subset on the sets. And they will all support a particular kind of reliable observation, in particular a threshold observation, where if I compare them with a constant and it's bigger than that constant, I know that that is going to be a true fact no matter how stale I am. In other words, if all my shared objects only ever grow and I only ever observe thresholds or stable characteristics, my resulting program can be correct and in many cases even convergent under weak consistency. And as a bonus, none of this relies on a transaction mechanism. None of this requires coordinated atomicity. It'll allow us to totally avoid all of those overheads we were worried about for consistent transactions. So normally at this point, when I'm trying to convince someone to say fund my research, I get a question. Yes, this is all very good, but can we actually build something useful with it? Just incrementing counters does not seem like a sufficient foundation. The answer turns out to be, yeah, you can. Many core systems components, especially at the protocol layer, are already fundamentally monotonic because they already rely on similar properties for correctness. Using this observation, we built a full system, Duratio. So I don't really have time to go into Duratio as a system, but it is a system-provided state machine replication via atomic multicast. It's basically one of those primitive libraries that you use to make a single machine, to make multiple machines operate in lockstep so that you can treat them as though there's just a single highly reliable machine. We managed to build a system that's significantly faster than state-of-the-art, offering similar primitives, and it's a real systems contribution. We gave our first tutorial on it at SOSP about 5 years ago. There's some stealth startups that are planning on using it. And I can't say more about the stealth startups because of the audience, but I'm happy to talk to you guys more offline. And at the core of Duratio is a small domain-specific language that leverages monotonicity. Okay, rather than show you the details of this language or walk through exactly what is or is not allowed, I'm going to do basically the same thing as last time and start with an example protocol that is required for any replicated state machine system. This protocol is stable message delivery. This part of it's really simple. So if a message arrives at one replica, we need to guarantee that it's sent to all replicas before any replica can react to it. So the way the protocol works is we take the message, forward it on to the two replicas. Those replicas generate confirmations, forward those confirmations onto the entire network. Once the entire network gets all confirmations, we can deliver the message and proceed with the protocol. And this guarantees that the message will only be acted upon if all replicas remain healthy and the message is received at all replicas. We're going to implement this protocol in terms of a simple shared state table. You can think of this as a single, centralized, globally accessible table, which we will not keep centralized for long. In this table, columns correspond to individual data items that we're replicating, and rows correspond to machines. Each individual cell will contain a monotonic object, like a counter or set, that supports a monotonic update that you can run any monotonic functions on, and that allows these primitive threshold reads. And we have a custom domain-specific language, once again embedded in C++, that'll guarantee this is followed. Let's look at how to implement stable message delivery in terms of this table. So we start with a message arriving at machine A, and we mark in the cell for machine A that the message has arrived. Those messages are then forwarded to machines B and C, which will cause those machines to mark in their rows that the message has arrived for them. Concurrently with this, we're running in a loop a computation to check if the minimum of the column received from A is at least 1. Now, minimum is a monotonic operation. It only ever goes up in response to the data going up that it's provided with. Once this is at least 1, we know that that first message has been received everywhere, so we can actually stably deduce that the message has been received. And we can proceed with the protocol, marking that message as deliverable and having the application react to it. So far, so good. But this relied on a single centralized table, which is exactly what we were trying to get away from. In practice, we're going to be able to implement this on a replicated table. So let me walk through this again on a replicated table. So first off, a message will arrive at A, and we'll mark that it has been received. Then that message will arrive at B and C, and B and C will mark in their replicas of the table that they received this message. So far, so good, but of course, no particular table actually has all the information. So we're still trying to check on that minimum of column, but no one can actually proceed because no one has local justification for it. Eventually, based on the properties of eventual consistency, we're guaranteed that the writes to these tables will propagate to the other replicas, and we will see their effects, which means that at some point, at least all of the participants are going to see that the column is at least 1. And we can proceed with delivery. So using just tricks like this, we were able to build strongly consistent consensus, the ViewStamp replication protocol, atop a weakly consistent underlying shared state table. And because we used a monotonic DSL to program that table, we were able to get strong theoretical results, like the overall convergence of our protocol and the race freedom of our individual concurrent programs, entirely for free, provided by construction, by the language. We know it holds just because it compiles. It's a perfect example of how careful language design allows us to build better systems. We managed to create a complicated system. We made it faster than the state of the art because we could remove a bunch of code that was, pessimistically checking to make sure concurrency violations weren't there, since we knew they weren't. We made it simpler to verify because now we don't need to care about multiple interleavings of our individual threads of execution, since our monotonicity result says they shouldn't matter. And ultimately, the code's shorter and more maintainable as a result. And this is, I think, much less researchware. So if you wanted to take a look at this project, you can head over to the GitHub page and download it. I will say most of the new development for it is under the Cascade label, which is the connected to one of the stealthy startups that's trying to launch based on it. So a bit of a whirlwind, but we have seen that monotonicity can work. But of course, it can't always work because ultimately not everything is monotonic. Remember way back in the beginning of the talk when I talked about how we use transactions to solve races and concurrency and how that's kind of expensive because we need to do that transactional coordination problem? I told you to put a pin in that. Let's take that pin out now and let's talk about races in shared memory again. This time returning to the simpler world of a single shared memory machine with our last and extremely brief section of the talk. I built a type system that is able to provably eliminate all destructive data races at compile time without requiring complicated user reasoning or annotations and without introducing any excessive runtime overheads under the hood. Think of it as the sort of guarantees you would have gotten from a language like Rust, but with more expressive power. And this is a paper in PLDI 2022. It's also what the bio was alluding to in terms of running on Apple devices. So what's this type system going to do? It runs in sort of a traditional imperative setting, so what it's going to primarily enforce is mutual exclusion. We want to make sure that all of memory is going to be accessed by a single thread at a time. Our setup is basically this. Individual threads, like the gray thread or the orange thread, will have private regions of memory that only they ever access. There will also be some shared regions of memory guarded by locks. Individual threads can temporarily gain access to that shared memory by acquiring the lock. So far, so good. But also, again, pretty common. We know how locks work. We've been using them since the 70s. And the challenge in compilers is not making sure that people remember to acquire locks before they access things. That's relatively easy to do. The challenge is figuring out when people are safely allowed to release the locks they've acquired. To see why, let's look inside our memory for a second. See, during the time the gray thread is holding the now gray, previously yellow lock, it might have mutated its memory, and it might have mutated the lock's memory to form references that point between the objects that it owns and the objects that the lock guards. And that's totally fine. I mean, that's the point of acquiring a lock, is to be able to mutate and access memory. But when we go to release the lock, we're going to need to guarantee that the gray thread doesn't try to use any of those references that pointed into the lock's memory. We'll also need to guarantee that any subsequent acquirer of the lock doesn't follow any references back to the gray memory that the gray thread left behind. In other words, we're going to need to track all of the references between these objects in memory in a dynamic imperative language. And it turns out that problem is undecidable. But that's okay. This is programming languages research. Most problems are undecidable. We solve them anyway. And this particular problem has been solved a few times before, most popularly by Rust. Rust's solution here is simple. For objects in the heap, let's just only allow trees. That means that when Rust has to consider the problem of tracking references between locked objects and owned objects, all it has to do is find the single incoming reference to each object. And that's a much easier and much more decidable problem than finding arbitrarily many. So good, we've solved it. There are no races anymore. Thank you, Rust. But there are still some data structures that produce problems. You see, it turns out not everything we might want to write is a tree. Consider, for example, a circular doubly linked list. This might be a natural thing to want to write in Rust, so I might Google around asking, how would I best implement a doubly linked list in Rust? And after sufficient searching and hand-wringing and being told about something called the stacked borrows paradigm, or that I can use an interactive proof assistant to be sure this is correct, I'll wind up being directed to code that looks kind of like this. This is awful. I mean, beyond the questionable choice of angle brackets and the fact that it didn't syntax highlight it, each of these individual layers of types is adding both runtime overhead to track something that we actually don't need to track if we understand the algorithm correctly, and it's adding code complexity. And ultimately, it's also cheating. I've said that I wanted to make this work in safe Rust, but each of these libraries is going to use unsafe internally. So ultimately, I'm just relying on these library writers to have solved the problem that I didn't manage. I don't think this is an acceptable place to leave things. So I went out and I built a new language. And I think I did better. Single keyword, no weird layers of type wrapping, natural code. So what's the big challenge that I had to solve to write my version of this language that Rust punted on? That challenge is something I like to call path confusion, which occurs whenever two syntactically distinct paths through an object graph may or may not point to the same place. And it's worth noting that this particular confusion is impossible in trees, so Rust can just not have it by construction. To see what I mean, let's turn to this circular doubly linked list in detail. Here I've written the circular list code up on the top right in a Java-ish style. We've got a list node prev and a list node next, represented by the blue arrows between the blue circles. Blue circles are the list nodes. The prev and next pointers are labeled. We've also got a payload, which has been annotated as ISO here, and is dangling off of each individual list node. This represents the thing that is stored at that position in the list. The ISO here is an important keyword from my language, which says that this thing is effectively isolated, that there's only one pointer pointing into it. Okay, now let's use this code. What our type system needs to do is be able to analyze any piece of usage of this code and tell me whether it's correct or not. So here's an example usage. We're going to start by taking a temporary on the stack and pointing it to the head of our list. Then we're going to take another temporary and point it to the second element of the list. Then we're going to send the payload to thread 1 and thread 2 respectively. And then our thread that has our list will exit to prevent races between thread 1 and thread 2. Now what our compiler needs to do is tell us whether this code is correct. So I'm going to once again take about 30 seconds to ask y'all, do we think this code is correct? There's maybe a bug, maybe not, but what are we feeling?
Is there the external consistency between the two threads that you're assuming? I mean, there's a
So
race in which one comes first, right?
for the purposes of this argument, we're going to assume that the list at the beginning of the code segment is only accessible to the sending thread, that thread 1 and thread 2 are freshly spawned and have nothing in them at all, and that the only data objects I'll have access to is head.payload for thread 1 and second.payload for thread 2. And then our sending thread will exit, so it's not going to race with them. We also know that there's exactly one reference that points to the payload. That was that ISO keyword. So there isn't some secret backdoor hanging out inside the payload that points back to itself or something like that. So do we like this code? Do we want to compile it?
The thing I can see is if you maintain, I think, what I might call a tree condition here, which you've got it because these things are isolated, that works fine. But whenever you have a transaction that includes payloads from more than one of those boxes, then you could get into trouble.
You can get into trouble anyway, it turns out. Because while I did have a tree condition on the payloads, I didn't have them on the list nodes. What this code needs to be correct is it needs list.head and list.head.next to be different objects. Because if they're the same object, then sure, the payload is unique, but I just got to the same pointer 2 different ways. So consider, for example, this data structure, where this is a totally valid instance of the same structure. Next and previous, these unconstrained pointers are self loops. ISO is still ISO. There's still one reference into that payload, but it doesn't matter because head and second are pointing to the same object. So sending head.payload and sending second.payload at runtime is just the same send twice. This is bad. We've wrongly assumed that head and second had to be distinct because I misled you by showing you this cool little graph. So reasoning about those sort of paths through the graph requires us to look not just at the actual data representation, but also at the representation at the level of just the ISO references, effectively erasing, or rather effectively collapsing every object linked by non-ISO references into one big equivalent set. This is what the compiler does. It looks simultaneously at this picture, in which it's very clear that head and second could be aliasing. And it also looks at this picture, and it only allows code to compile if it's safe under both abstractions. And again, this ISO keyword establishes statically enforced boundaries. So that's the one where you actually get the sort of incoming uniqueness or external uniqueness condition. Now, there is a cost to using this method. It doesn't completely solve all the problems of representing data structures. And in particular, it means that we can't actually distinguish between the head and next and previous statically in this list at all. So if you as a programmer happen to know for some reason that they weren't pointing to the same place, the compiler wouldn't know that you knew that. The compiler wouldn't be able to have access to that information. Now you can introduce it dynamically. We have a keyword if distinct here that basically says, we'll do a runtime check to make sure that these are actually different objects, which then implies that they have different payload pointers. And if we do that, we know that there are 2 distinct payloads and we can actually do the sending. So that would solve our problem. I would point out that if you're using any doubly linked list in any language, you do want to do this check before assuming that there are 2 elements in the list, since there's nothing about the data type that tells you it has to be at least size 2. So while this is a dynamic check, it's the exact dynamic check the algorithm already required. If you want to be especially fancy, and you want to claim that not just our head and second distinct nodes, but they're now completely disconnected. I've done some operation to split the list. You can use a more complicated primitive if disconnected, which checks to make sure they're mutually unreachable. And in that case, it'll allow you to treat the entirety of the list rooted at head and the list rooted at second as distinct objects. So using our primitives and our analysis, we were able to build out a language and a library that features all the standard things you want to do on collections, including several operations that were not possible to implement in any safe previous language. And it works. It's significantly low programmer annotations. The compiler error messages are friendly enough that people can figure them out. And it doesn't introduce any runtime overheads unless the programmer explicitly types words that suggests that runtime overheads should occur. After writing the paper, we wound up proposing this for Swift. Their proposal was accepted, and it's now going to roll out in the next major release of Swift as part of the new Swift concurrency model. So we're extremely excited about that. And there's already millions of lines of code that are testing and using some of these features. And that's basically where I want to leave you. We've built a large number of distributed systems over the last few years, demonstrating that by entwining careful language design and careful system design, and by approaching both problems together, you can make better systems, faster systems, and more correct systems without sacrificing your sanity or your runtime overheads. Thanks. Now's a great time to switch to discussion.
Thank you very much. Congratulations for your work that is now adopted by Swift. That's really an amazing achievement. All right,
yes, I got very lucky on that.
No, I think this is the luck that, like, when you have hard work, it's a justification of your, like, it's a humility thing. So let's start, open the floor for questions. I see Paul, I think, is ready for it, right? Paul, go ahead.
First of all, Mae, that was an absolutely fantastic talk. Thank you. I am so pleased that you've done this. I can point everyone now to your work. But a little bit of history. I was in Apple when 9 years ago when Swift was introduced, and all of the problems you're describing here were the problems I was running into. My question here specifically is, can you add this is there a way of adding it to Rust?
It's a bit complicated to add it to Rust. So we tried to, Rust has a notion of ghost state and ghost cells introduced via library that Ralph Jung, who's at this point key maintainer for the consistency of Rust in general, was able to introduce in a paper a year or two ago. And it tries to do a similar looking thing where it creates a closure scope in which you're allowed to create arbitrary pointers that create graphs, and it then at the end of that scope encapsulates them all behind a single reference. We tried to actually mutually embed our work into each other's work. And Ralph was able to embed his stuff into ours, but we discovered several expressiveness limitations with Ralph's approach that prevented it from actually reaching the power of our approach. You could change Rust's type system to use this. In fact, if you look at it and you just say, what if we just put ISO everywhere, you'd wind up with a very similar amount of power to Rust's type system. But it's not the sort of thing you could add via a library. It really would be a fundamental change for the language, much as it was for Swift. So not incompatible. We'd probably change where the keyword went so that the existing Rust code didn't suddenly need to get peppered with keywords. But it would require like a language level change that probably is a major release and needs all those stakeholders to get on board.
Interesting.
Thank you.
It's also worth noting that there's a bit of an issue with garbage collection intersecting with this approach. Yes. Our approach was entirely for concurrency. So when I have these non-ISO references, they can form arbitrary graphs. And that means that there's not a static point at which me nulling out one of those references or me self-assigning one of those references is guaranteed to eliminate all access to the previous target. If I had a tree, the uniqueness property would mean when I assigned away from something, then I was guaranteed that I've eliminated its only reference, so I could immediately delete it. Under this scheme, we don't have that guarantee. And our solution as currently deployed is to use reference counting because we're currently a Swift target. And in particular, we actually make reference counting faster because you can use the granularity of those ISO references to determine when ref counts may or may not be concurrent. But I don't think Rust as a language would be all in for, yeah, let's add reference counts to a class of references. So you'd need to come up with a different solution for memory management in that context.
So I have a question. Sorry, Paul, you have...
No, you go ahead. I was thinking if no one else has a question, I have another one, but Ahmed, please go ahead first.
Sure. So one thing I was wondering is as the number of nodes increases, the complexity, of course, increases, and like basically that propagation you were showing. I was hoping like I understand a little bit more like from your slide 74, like the propagation of those ones as they go through. Like, what's the mechanism? Like, and how much should I wait for? Because I look at everything at like states, right? And I look at the whole system as one state, and I'm figuring out how the propagation of this subsystems together gives me that ultimate state. So I have a wait time always to get there. So how what's that mechanism? Is like you have to wait for everyone to go through? Is it like similar to like the 3 phases you have in Paxos, or you have by default when you get something you have to send it and then you have it's like commit and wait, like there's a certain time that you have to wait at least for the data to propagate, worst case latency. And I mean,
So
there's a statistical approach everywhere.
It depends entirely on what you want to make your network assumptions to be. So we actually have 2 implementations of this. We have a basic like circa 1988 TCP implementation, and we have a RDMA implementation. The RDMA implementation is way easier to work with. You have known latencies, you have guaranteed delivery times, you have guaranteed delivery windows. So you can actually use an extremely efficient failure detector to allow you to make progress after modest amounts of delay. The classic 1988 TCP version has everyone's favorite result, the Fisher-Lynch-Patterson result, haunting it, effectively saying that we can never conclude that the message is done being delivered. I will say, though, that what we're replicating here is state, not messages. So as the message complexity of the system increases and as machines fall behind, what we're trying to synchronize to them isn't all the messages they've missed. It's just the new result of the table. So if you missed 16 distinct increments, I'm just going to try to forward you the number 16. So the catch-up winds up becoming a little bit more efficient than you'd expect that way. In practice, the way this works, if there is a particular slow machine and that slow machine is not too slow, then we're just going to wait for it to get our message every time before we make a delivery. It's state machine replication. We need the guarantee that the machines move in lockstep. So the slow machine will keep moving in lockstep. If that machine is too slow, there's a failure detector thread that can time out, and that will effectively cause us to copy our entire table into a new state. Logically copy, we reuse the memory. And then that new state doesn't have the slow machine and we can exclude it for the future. If it ever wants to reboot and come back, it can reboot and come back. But yeah, fundamentally, it's SMR. So while we are efficient about making sure we're synchronizing state and not messages, the protocol's purpose is to make, say, you, me, and Paul all have the same information. So if Paul takes a day and a half to tell us he's got it, our choices are wait or exclude him.
And like subsequently, let's say if you are tracking entropy, I mean, with a monotonic counter, also known as precise time, would you be able to take advantage of that? And let's say, I mean, you will probably let go some of your reliability and handshakes with watching basically who got the like latest timestamp and so on. Is that something also, I mean, can take advantage of this? Because again, I'm a hyperscaler. I need things with a lot of zeros, a number of zeros in front of it, right? So when I go in scale, can I rely on basically a physical clock versus logical clock?
So if you are a hyperscaler, you're getting a phone call, by the way.
No, that's not me. That's Hisham. I muted him.
Thank you. Sorry, Hisham's getting a phone call. If you're a hyperscaler, then you probably shouldn't be implementing SMR.
Yes.
As a protocol, it's just not a great choice. So we don't have some secret sauce that makes your machines be able to like reach into the void and grab data faster than the speed of light could replicate it. That would be cool, and I would have a Nobel Prize. But what we do have is an underlying monotonicity result that basically says if you can use a monotonic program, if you actually only care about thresholding things, if you only care about growing things, then you don't need to wait for synchronization. So most of the places this has been deployed is actually in the geodistributed context.
Yeah.
So a simple example of this is, let's imagine for a moment that I'm trying to replicate user data hyperscaler across multiple continents, and the user data is Google Docs style. There is a dynamic evolving set of users that actually care about being synchronized. They're usually order 10. For a very rare occasion, they're order 100. Geographically speaking, they're usually order 2 in terms of data centers that need to be synchronized. You can actually use true time hacks to keep those data centers synchronized, and then use monotonicity for the rest. Keep the rest of the world locked to only the monotonic observations. The natural result is that you actually do get full possibilistic guarantees. It's no longer a probabilistic fallback, but what it is a probabilistic limitation. It may be the case that some user on an airplane or some user somewhere else gets a view-only mode or gets a potentially stale mode, but they still get exactly the guarantee of what they're seeing. So I tend to like that. I tend to like putting the probabilistic fallback on the power that we're going to give the user rather than on the results that the user's writes will have, since it's just easier to reason about.
That's right. Fair enough. Thank you. Thank you.
Sure.
All right, let's go next. Hasham, go ahead.
Yeah, I have a question for May. Thank you very much, May, for excellent presentation as usual. Have you thought about time synchronization for strict consistency?
So how to best synchronize time for strict consistency?
How time synchronization can help strict consistency?
So I'm tempted to say here, not even a little, but what I mean by that is my work is entirely about how to erase the dependence on time and how to break the correlation between time correctness and data correctness. I'm trying to find more and more programs that are safe under stale data. Because if I can find more programs that are safe under stale data, it's dramatically cheaper to deploy them and maintain them. And ultimately, you will need a portion that's safe under only synchronized time and requires there to be tightly synchronized accesses for sort of a strict linearizability plus semantics. But I would much rather know that section of the program, minimize it, and invest our resources there, invest our careful engineering there, than just kind of try to move an entire application to assuming that this abstraction exists. Putting it differently, I know a lot of you folks are hardware folks. There's always a temptation when we build new hardware, when we build new systems, of trying to provide exactly the abstractions we had 30 years ago. And sometimes you can do that and it's brilliant, but usually you're giving up on some power that you could have had by providing honest abstractions. Usually you're being conservative in a way you don't like by providing these old abstractions. I'm willing to change the language and the programming a little bit so that you still write in something that looks like Java, but the compiler is more angry than usual in order to provide the abstraction of what's really happening at a higher level, and hope that we can write faster systems as a result.
Paul, go ahead.
My final question is, if you had access to the hardware and design, like, for example, new CPU instructions that you could add, or new network protocols that you could add, you've already mentioned RDMA, would that be helpful to you?
Yes. So if we could get guaranteed routing, that would be extremely helpful. There's a lot of this results that I was talking about under monotonicity. Monotonicity is a pretty limiting thing to acquire. There's this old result from databases called the CALM results, C-A-L-M. which you can argue whether it holds or not, because the transducer model it was formalized under is really bizarre. But the summary is, if you have this really weird networking setup where all the messages can get sent to anyone in any order, and you have no assumptions about delivery, and you have no assumptions about routing, that's the best you can do. But as soon as you have routing assumptions, as soon as you can say that like a message will go from me to Hisham to Paul in that order every time, you can start allowing much more expressive types of programs without introducing any new synchronization requirements. Similarly, if we had access to hardware primitives for doing things like actual monotonic messaging, it would be a lot easier to write programs that didn't need to rely on strict mutual exclusion analysis for their correctness. If you look at the old Itanium model, which was itself based on like the 1988 era multiprocessing model, they have in memory the idea of sequential consistency, release, acquire, relaxed, and consumes, which no one ever uses, as their consistency layers. And those are just kind of like what the hardware folks thought of. And for 30 years after that, programming languages folks have tried to translate what the actual users would need from their guarantees into those 6 models. If we could just toss that out and try again, looking at that research and thinking, how do we directly implement what the users have needed as their guarantees, then we would be able to much more efficiently implement half of these primitives.
Fantastic.
Tech debt. We call it.
It's somewhere between tech debt and communication breakdowns. We can't all be experts in everything, but it's all too easy to allow ourselves to talk to the people that are experts in the same thing as us too often.
Yeah. The bridging is important. Yeah, I agree with you. All right. Any more questions?
I think we're at the top of the hour. So I'm going to keep my mouth shut until I speak to you privately, Mae.
Sounds good. I'll put my email address in the chat just in case people don't have it.
Okay, thank you.
If you can also put it in, do you have it in a slide? Just put it in a slide, so because people have access in the recording to the.
You know, oddly enough, I don't, but I also have a computer, so I'll just open up Notepad and call it a day.
Because people usually see the recording.
The chat's not included in the recording?
I don't think so, no, because this is a YouTube thing, right?
I have no idea how this stuff works.
No, it gives me something to upload on YouTube, yeah.
Well, here, I'm sharing a Notepad with my email address in it.
Wonderful.
And also a notification of my next meeting in it. Sorry about that.
All right. Great. All right. Thank you very much again. And hopefully you tell us if we can have another like subsequent call about, let's say, where we can take it, because you know, like this group is like a special interest in precise time, and we see like how we can now utilize physical clocks and how we can take advantage of that as well.
I'm happy to jump in on a call about that. I do not have like 5 years of research on it.
Yes.
It's not really my area, so I won't be able to prepare like a complicated slide deck. But we can talk offline about how to best use that.
Wonderful. Thank you very much. All right.
Thank you for your time.
And see everyone. So Dan, go ahead.
I'd like
I was just going to say thank you for your time. I appreciate it.
Thank you, Dan.
Culture for this and I'd like to propose that we do a round of applause when we've seen a really great talk.
Thank you. All right, so we'll see everyone coming Wednesday for call number 110. I forgot the topic. Oh, it's actually about spike neural networks, which is basically by Jason, which is basically a neuromorphic approach to do neural networks by Professor Ashraqian from University of Santa Cruz. All right. Bye, everyone.
See you all.
Bye.
Thank you.